And we now move into the examples of Chalmers research activities that links to sustainable materials. And we start with Karin Lundgren, who's a professor in concrete structures, and she's working on then large amounts of materials, one could say. So I'm sure it's going to be delightful. Welcome.
Thank you. So let's see, here was the clicker. So great, thanks. Nice to meet you all. Let's see, that was my slide. Actually, when I stand here, I hardly see you because I only see the lights. So this is kind of interesting. So Karin Lundgren, just as Leif said, professor in concrete structures, working here at Chalmers. And when I decided, I was asked about the title of my presentation. And I realized that this will all be about sustainability. Should I have sustainability in the title? And then I actually decided, no, I won't, because I will speak about materials in civil engineering structures. And civil engineering structures, I think not so many of you are working with them, so I start by presenting that. And I would say that I think most of you would actually be surprised to hear about the requirements we have for the materials we're using in civil engineering structures. So compared to most other applications, we have very, very large volumes required, and we have very, very long lifetimes expected and required. So a bridge, this one is Tornebergsbron in Stockholm, is 90 years almost now. And new bridges we build today actually have a requirement of 100 or sometimes even 150 years of lifetime, which is way more than when I buy a cell phone. I don't expect it to last for 100 years, at least not yet. So actually, sustainability is always in focus if you speak of civil engineering structures. And of course, it also holds for the materials we're using, because they are in such large volumes and because they are expected to last for such a long time. And when I've been working with, so I'm actually a structural engineer, I'm not a material scientist. So I feel a bit like an outsider here, but I've actually been moving towards the material science, I would say. So what I've been working with is actually both existing structures and new structures. And with existing structures, it's typically bridges, because they are supposed to last for so long time. And what's important then is really that we can manage to keep them as long as possible. So I would say that's the major sustainability gain, that we can continue to keep whatever we have for additional 20, 50, perhaps even 100 years, instead of producing new materials, producing new structures. And there I've been working quite a lot with deterioration mechanisms and how you can forecast how long time a structure will last, and also to even know the status of it today. And I will also speak a bit about new structures. And then, of course, the main focus from the material aspect is to have material which doesn't have too large carbon footprint. I'll come back to that, but I will actually start with the existing structures, where I have put most of my effort, I would say. But as I say, I'm trying to stand on both legs here. But starting with the existing structures, and what you actually also need to consider, also for new structures, how will this one grow old? So growing old in a beautiful, natural way is important. And the main deterioration mechanism for reinforced concrete structures is really, it's not the concrete that is the problem, it's the steel. I keep telling the professor in steel structures that all the time. Because the steel corrodes. I mean, you would think that the high pH of the concrete really prevents corrosion, and it does in the beginning, but not in the long run. So sooner or later, corrosion will start. And what happens when corrosion starts is that corrosion is a swelling, has a swelling effect. So the rust has a larger volume than the steel it was made of. And that will cause pressure to the concrete and eventually crack the cover, as we see here, and eventually even spalling. So if you look at what it looks like in reality, you see from below of a bridge, it can look like this. And then, again, I'm a structural engineer, so what I ask myself is, of course, how much reinforcement is still remaining? I need the reinforcement to carry the tension load. So concrete is great in carrying compression, but we need the reinforcement to carry the tension. So how can I assess this one? How can I tell whether it's safe or not? And you all have seen the news of the Morandi Bridge a few years back when there was this huge collapse because they actually had misunderstood. They knew very well that they had corrosion going on. They thought they had repaired it, but they had totally misunderstood how much corrosion was going on. So that was really what caused that failure. And one idea we have then, and I'm definitely not alone on having this idea, is that it would be beautiful if we can see from the crack pattern on the outside, to use that as some kind of idea of how much corrosion damage do we have internally. Because if we know how much steel we have lost, then it's an easy task to calculate the remaining capacity. That I can do as a structural engineer. But to know the level of damage, that is really the key. And trying to link the crack pattern on the surface then with the internal damage. So what can you do? Well, you can try to model this. I mean, I'm a scientist. Of course, I want to model things. So devise a model which includes the swelling action and model the cracking of the concrete. I mean, you need nonlinear fraction mechanics and all that stuff, but that's the easy part. I mean, when I started as a PhD student, nonlinear fraction mechanics, whoa, that was difficult. But starting with this one, I realized there were so many other phenomena involved. Like the ones I'm lining up here, you need to know about the rust versus the steel, how large is the volume expansion. You need to know that there's a bit of a porous zone surrounding each bar. And if the rust just grows in this porous zone, it doesn't cause any, well, it causes swelling, but it doesn't cause any stresses yet. So we need to know how big that one is. Next one in line is the mechanical properties of the rust itself. I mean, it wants to expand a lot, but the concrete will push it back. So depending on how stiff the corrosion products are, you will get small or large stresses. You need to know if the corrosion can escape. It may be able to be transported even through the porous media, which concrete is, and even more so when you get the cracks. Can it escape through the cracks? And is the corrosion products even soluble, so it can kind of be washed away? We also have this effect of that you get, if you have, especially if you have chlorides, you will get something like pitting corrosion, so you will get not just corrosion all the way around, but more at certain spots, so to say. And the spots are both around the bar, but also along the bar. So these will really influence the crack pattern. And the effect of flexural cracks, it's a 3D symptom, and so on. So there's so much into this. And what actually turns out, I started working with this roughly 20 years ago, and you can do this. I mean, I modeled this. But what I did and what everyone else have done is to calibrate models for this just based on what we can see on the outside. So all we actually have is that we have corroded specimens, we have measured the crack width, and then we broke them and saw how much corrosion we had on the inside. But that really, really limits us, because it means we need to guess so many values that you actually can calibrate it in many, many different ways. Too much unsecurity involved, so to say. So I actually more or less dropped this and said that, okay, fine, you can do something, you can get it roughly correct, but we are more or less just guessing. But then, a few years back now, we started working with X-ray and neutron scanning. So people have been trying with X-ray on beforehand, and it wasn't good enough. But now when combining it with neutron scanning, we can actually see the inside. And what we've been doing then is that we've been looking, in this example, we've been looking at both artificially corroded samples and naturally corroded samples. And the artificially ones are specimens which we cast and then put current through so that we were in control of the whole specimen and knew how much corrosion we had and so on. While the naturally corroded ones, they are pieces that we took from an existing bridge, 80 years old. And you can imagine all the challenges there. Of course, you're not in control with what kind of material you have. Of course, you're not even in control of if you have a corrosion going on in the piece you have. We simply had to chance. We knew that there were lots of corrosion going on almost everywhere, but not everywhere, so we had to drill cores and kind of chance that. Let's hope we have some corrosion inside here. So then we did, as I said, both neutron and X-ray tomography. And by using phase segmentation, we could actually divide the constituents, so to say. And we could, you see the different colors for the different parts. You could see the aggregates. You could see the cement paste in between. We could even see the corrosion. So the dark blue parts are the corrosion, and the red one is the steel. And you see here to the left is the naturally corroded sample, and there we typically had lots of corrosion at the void. That was really what we saw. While for the artificially corroded samples, when you're running current through, you're forcing the steel to corrode all the way around. And that's yet another challenge that almost all research is done on artificially corroded specimens because you want to be in control of what you have. But that is not what we're actually interested in. We want to know about the real structures. And probably we need to work with both to actually get all the way. What could we get out of this then? Well, we could actually get a lot of, in addition to the nice colorful pictures, which is of course always nice. I know people who have been speaking about color mechanics since a number of years, but you can also get numbers out. You can actually get things which you can use in modeling later on. So for example, we were able to evaluate the volume expansion. And we did that by looking in single corrosion pits at air voids. So when there was a corrosion pit, so the light thing that shines out here, it's the corrosion. It's light and shining. That's how I like to see it instead of brownish and ugly. And we could, from the 3D, I mean, now you are showing it in 2D, but you have to imagine that this is actually a 3D scan. So we could calculate the volume of the corrosion products. And we could, of course, also calculate the volume of the steel that was lost. And from that, we could estimate the volume expansion. And I don't know if you see the numbers, but for the naturally corroded samples, it was around 4. For the artificially corroded sample, we managed to find one such corrosion pit with one such void, and estimated slightly less, 3.9. I mean, it's roughly the same. But what we also did was to try to evaluate for the whole sample from the artificially corroded one. And then it's about 2. And that's interesting, because that is what most people have been using in analysis. But what we don't need to consider then is that, well, that is not the free expansion. That is the expansion that it managed to create because it was compressed back by the concrete. So how to express this in modeling is not completely straightforward, I would say. But I think that the free volume expansion is something we'd rather want, and want to know the mechanical behavior of the corrosion as such. We could also see how the corrosion is distributed. And as I said, typically for the naturally corroded samples, we saw that it took place at air voids instead of spreading out all the way around. And in ongoing, so the ones I showed there was from my former PhD student, Samantha Robushki. Now in ongoing work, Andreas Alhede takes over, so to say, and continues. And what he's looking at is actually, the examples I will show here, is the same specimen which we scanned twice. And in between these 2 scans, we put on accelerated corrosion. And I don't know if you've been in Grenoble and been using the fancy equipment there. You know that it's not very easy to get your hands on that equipment. So once you're there, you want to get as much as possible out of it. So this specimen was very heavily corroded just overnight. So it's way too high current, way too large corrosion rate to be realistic. But we mainly wanted to check whether it's possible, what we can get out of this kind of methods. And what you can see here on this axis is the corrosion level, the dark brown, and on the x-axis is the length along the specimen. The dark brown it was actually corroded already first time we scanned it, so that's the corrosion level from the first part. And the light one is after the night, so to say, after subsequent corrosion. And we can see how it varies along the length. And what we managed, and I should say that this was really not super easy to manage. I can say that Andreas really struggled before he could solve this. But he could manage to actually follow each pixel with digital volume correlation so that we can get the whole displacement field. And it's not just as easy that you put in the scans and then you push a button and then it's done. He really needed to work a lot with different kind of filtering and everything. But in the end, what we see here is the displacement field. And you can see how this upper side here moves in this direction, and this lower side moves in the other direction. So what we typically see is a crack taking place here, or opening up even more. And when we see it here, of course, we mainly see the outside, but we can really cut all the way through. So we have a 3D movement. We know the displacement field in the whole 3D specimen. And what we also could do, just like we did before, we use this phase segmentation to actually divide. And we can actually, from the neutron scanning, it's also quite easy to see just from the figures, so to say, what is what. But if you look close to these ones, you see the aggregates and you see the cement paste. But if you look closely, you can actually also see that there's some brownish color, which Andreas used to show what was the corrosion products. And I don't think it's visible. I can't see it, but I have bad eyes. You can actually even see the cracks. He managed to get the cracks also through phase segmentation. And what is so nice is that you actually can see through this displacement field, you can also derive the whole strain field. So you can actually view in different slices along the specimen how the crack looked like. And here, for example, you see the strain localization due to the cracks. And these types of contour plots, if I say so, is what we've typically been looking at from analysis for a number of years. But what we can do now is really to have experimental results to compare with, to be able to come back. So if you remember this slide where I had all these phenomena lined up, what we're interested in, but what we want now is really to be able to base them on measurements instead. And so now suddenly I would say we actually have a method to start doing that. And I mean, these methods, they really then move towards material science. And I guess that's why I'm here today, because we show how we can actually link these different worlds, so to say. Moving back again, one step further back to my previous slides, I promised I'd say also something about new structures. And as I said, then it's really, really important to use materials with a decreased carbon footprint compared to what we're using today. And why is that so important? Well, as I said in the beginning, for civil engineering structures, sustainability is always an issue. Actually, I mean, so much of the CO2 emissions we have is due to cement production. So you can view that in different ways. You can say that, oh, the cement producers, they are just the big thieves, and we should not deal with that. And actually, the big CO2 emission is also because it comes from the heat production that is required, but it also comes from the chemical reactions. So it's really, I mean, you can think of different ways to make the heat production as clean as possible, but the chemical part of it you will kind of never get rid of if you want cement production. So why do we then use cementitious binders? Why don't we just drop it and build everything in timber structures instead, or whatever you then want to claim? Well, first of all, not all applications are doable without concrete. And it's also so that concrete is really, it's the cheapest building material used in large volumes. We can't find anything better, simply put. And it's also so that it's available more or less all over the world. So, and that, of course, is the reason why it's used so much. I mean, it's only water that we're using more of. And that's kind of amazing, I actually think, that it's in such huge volumes that it's hard to understand. So we actually, it's not as easy to just say, let's stop using concrete, let's stop using cement. But we need to look for ways to improve it, to make it better. And one way to go is to use supplementary cementitious materials. So trying to replace as much as possible of the cement with something which is more friendly, so to say, which doesn't give away so much carbon emissions. And what's traditionally been used is actually the two upper ones, slag and coal fly ash. And I would say in Sweden, I don't know if there's someone from Cementa here today, but let's simply put it like this. Traditionally, there has been very strong arguments in Sweden not to go this path. In the rest of Europe, or even internationally, it's been used quite a lot. So I would say most other countries really have lots of experience with using both slag and coal fly ash and feel rather safe about that. Anyways, that's kind of more or less irrelevant because we will soon run out of them. As long as you produced slag just as a by-effect when you were producing steel, you could view it as super cheap and so on. But now suddenly everyone wants to put it in the concrete. And again, remember the large volumes? It's simply not sufficient. And we will also hopefully stop burning coal, so we won't get any more coal fly ash. So this is not the path to go. That's at least my idea of it. So what is then the path? Well, what I would believe more in is these natural pozzolans. And for example then, calcined clays or volcanic ashes. And I actually almost feel embarrassed to be here speaking about it because it's Aresu sitting in front who is the one who has learned me most about this actually, assistant professor in building materials, and you will get the chance to listen more to her tomorrow actually. But what we need to learn then, even though I feel embarrassed, I will still speak a bit about it at least, but please go and listen to Aresu tomorrow. So what we need to know then about these ones, before we can just start applying them, is that we don't know about their long-term performance. So then we actually come back to that, okay, we suddenly need to understand how do they work if you combine them with steel, and how do they work in themselves. And as I see it then, if we think of composites, and remember it's still composites, I mean, the supplementary cementitious materials in themselves, in a way they are actually also composites because they are made of stones and some kind of matrix. But to have them in civil engineering structures, you will still need reinforcement. They are good in compression, but you need something to take the tension. So you need some kind of reinforcement. And as I see it, I see two possible roadmaps. One is that you continue with steel reinforcement, and the other one is that you use some other type of reinforcement. I would then suggest carbon reinforcement. And with steel reinforcement, you still have this problem that sooner or later you will get corrosion, and for that you actually need knowledge on carbonation and chloride ingress. If you go the other path, if you say that, okay, fine, let's work with carbon reinforcement instead, well, we still would need knowledge on carbonation, because that actually comes with shrinkage and microcracking. So that in itself needs to be handled, and it's really crucial for these new type of cementitious binders. And also, if we go with carbon reinforcement, we also need to be in control of how it interacts with the matrix. So we will get interfilament slip, and we need to be able to control the impregnation of them. So just one picture of where we have these kind of carbon filaments, and you see that when they break, it's really not one unit as we used to with the steel reinforcement. So what we need then is actually to link different scales, going from micro to meso, all the way to structural. And again, I've been borrowing one slide from Aresu. When we're looking on the micro scale, she's way better than I am, but I've been working quite a lot with the meso and the structural scale. So just mentioning long-term collaboration with Industrial and Material Science, I think is your name today. Where we've been modeling in multi-scales. We started actually with chloride ingress. What you see is a figure of a representative volume element with a crack, where you see how the chlorides penetrate through a crack around the aggregates in the cement paste, and then we homogenize that. And in later work, we actually looked at reinforced concrete structures and looked at how we can model that in detail, still being able to describe the whole structure. And we just got a new VR project funded on this, on textile reinforced concrete, which is exactly the carbon reinforcement I showed before. So concluding, and I see that you have already you're already standing up. I'm about to end. For civil engineering structures, sustainability is certainly an issue. That's something we always have in mind. And we really need to think of the long-term performance because it's such long periods involved. And this thing, combining X-ray and neutron, will hopefully give us a chance to actually calibrate and understand what happens on the inside. So I leave it by that. Thanks a lot.
Thank you, Karin.